You know, we have this phrase, terra firma. It's our go-to metaphor for anything that's stable and trustworthy. You plant your feet on the ground and, well, you just trust it's not going anywhere.
It's the most basic assumption we all make.
Right. And if I look at a map, it feels permanent. North America's here, Europe's way over there, and they seem completely locked in place.
And for most of history, that was the scientific consensus too. The Earth was seen as a static thing, a statue. Continents were fixed. Maybe they bobbed up and down a bit over eons, but moving sideways, it was seen as impossible.
Which is exactly why the shift we're talking about today is so profound. It wasn't just a discovery. It was like someone handed us a completely new operating manual for the planet. We went from thinking we live on a solid rock to realizing we're all just floating on this giant moving jigsaw puzzle that's constantly rebuilding itself.
I think scientific revolution is the only term that really fits. It's on par with realizing the Earth goes around the sun, not the other way around. We're talking about the theory of plate tectonics.
And what I loved about the material we read for this deep dive, especially that breakdown in Chapter 3, is that it reads like a detective story. It doesn't just give you the answer, it walks you through all the false starts and the ridiculed ideas first.
It's a very messy history.
Yeah.
You have this theory that was, just laughed at for decades, and then it's resurrected by technology that was actually built for war, not for pure science.
So that's our mission for this deep dive. We're going to trace this whole story from the crazy idea of continental drift all the way to the verified science of plate tectonics. We want to get to the bottom of how mountains form, why earthquakes happen, and why the Atlantic Ocean is getting wider as we speak.
And it all started with a simple observation, not from a geologist, but from mapmakers.
Right. This goes all the way back to the 1600s. The second we had decent maps of the Atlantic, you can just imagine someone looking at South America and Africa and going, wait a second.
It's just unmistakable, isn't it? The bulge of Brazil fits almost perfectly into that big curve of West Africa.
It's the kind of thing you notice in fifth grade geography class. But for 300 years, the consensus was, yeah, that's a cute coincidence.
Until 1915. Enter Alfred Wegener. He's a German meteorologist, of all things, and he decides, no, this is not a coincidence. He publishes The Origin of Continents and Oceans and proposes that all the continents were once one giant landmass.
Pangea.
Pangea, meaning all lands.
Yeah.
He said that around 200 million years ago, it started to break apart and the pieces just drifted, hence continental drift.
Now, Wegener was smart. He knew that just saying, hey, they look like they fit, wasn't going to cut it. Coastlines change, they erode.
Right, it's not a smoking gun.
Yeah.
So he started digging for other evidence that would be much harder to just wave away.
And he found it in the fossil record, specifically with this one creature, the Mesosaurus.
That's the one. It's a small, sort of alligator-looking reptile. But the key detail is that it was a freshwater animal.
Okay.
And we find its fossils in only 2 places on Earth, Eastern South America and Southwestern Africa.
And absolutely nowhere else.
Nowhere. So if the continents were always separate, you have a huge problem. How does a small animal that lives in lakes and rivers cross 3,000 miles of salt water?
It doesn't. It can't.
Exactly. Now, critics at the time, they tried to explain this away. They came up with these ideas of land bridges, these long strips of land that supposedly connected the continents and then just sank.
Which we now know doesn't really work. Continents don't just sink.
Not like that, no. And it wasn't just animals. Wegener found a seed fern, Glossopteris. Its fossils are all over the southern hemisphere. South America, Africa, Australia, India, and Antarctica.
The Antarctica part always gets me. A fossil of a temperate plant buried under miles of ice.
It tells you right away that Antarctica wasn't always at the pole. But more than that, the seeds were too heavy to be carried by the wind across entire oceans. The only explanation is that all those continents were once huddled together.
So you've got the fit, the fossils, the plants. But I think the rock evidence, the geology itself, is the most damning part of his argument.
The mountain belts, yeah.
The Appalachian Mountains in the U.S., they run northeast and just disappear into the Atlantic Ocean. But then you cross the pond and you find mountains in the British Isles and Scandinavia that are the exact same age, the same structure.
It's as if you tore a newspaper in half. The lines of text just continue perfectly across the tear. He also found evidence of ancient climates that were totally out of place.
You mean the glaciers?
Massive ice sheets. He found evidence for them in places that are now tropical. Southern Africa, India.
Which makes zero sense if India was always near the equator. Why would there be a glacier there?
Right. And at the same time, the northern continents, North America, Europe, were covered in these lush tropical swamps that formed all the coal we use today. The whole climate map is upside down.
But if you reassemble Pangea,
It all clicks into place. The southern continents cluster near the South Pole, creating one big ice sheet. And the northern continents shift to the equator, right where you'd expect to find swamps. It solves everything.
So Wegener lays all this out in the 1920s. He's got the maps, the fossils, the rocks, the climate, and the reaction from the scientific community was
Brutal. They ridiculed him.
Yeah.
Absolutely rejected the whole idea.
And it's easy for us to look back and say, how could they be so blind? But to be fair, Wegener had one giant hole in his theory.
A huge one.
He knew what happened, but he couldn't explain how.
That's the crux of it. He lacked a mechanism, a force. You can't just say continents move without explaining what's pushing them. He guessed it might be tidal forces from the moon.
But the physics just wasn't there.
Not even close.
Yeah.
A physicist showed that any tidal force strong enough to move a continent would have stopped the Earth's rotation within a few years.
Whoops. Okay, so that's out. He also had the idea that continents were like icebreaker ships, right? Plowing through the ocean floor.
He did, but there was no evidence for it. No
Yeah.
crumpled, deformed rock at the leading edge of the continents, no scar tissue, so to speak. So without an engine, the whole theory was basically dead on arrival.
And the sad part is, Wegener died in 1930 on an expedition in Greenland, still trying to prove his point. Never knew he'd eventually be vindicated.
It took another 30 years, and strangely enough, a world war.
This is where the story shifts completely. We go from looking at rocks on land to mapping the deep ocean. And it was all driven by military need.
Exactly. Sonar technology. The Navy needed to map the seafloor to find and hide submarines. Before this, everyone just assumed the ocean floor was this flat, ancient, boring mud pit.
But what they found was anything but.
They found the global oceanic ridge system, a 70,000-kilometer-long mountain range that winds through every ocean on the planet like the seam on a baseball.
And that was the first clue that the ocean floor wasn't just a passive bowl. Something active was going on down there.
And then came the clincher, the magnetic stripes. This is maybe the most elegant piece of evidence in all of geology.
Okay, let's break this down because it's a little technical, but it's the absolute smoking gun. The Earth's magnetic field, it flips, right?
It does. Every few 100,000 years or so, magnetic north becomes south, and south becomes north. When hot lava erupts at those ocean ridges and cools into rock, the little iron minerals inside it act like compass needles. They lock into alignment with whatever the Earth's magnetic field is at that moment.
So the rock becomes a fossil compass, a recording.
A perfect recording. And what they found were these mirror image stripes on either side of the ridges. A stripe of normal polarity, then reversed, then normal, then reversed. Perfectly symmetrical.
Which can only mean one thing. The seafloor is spreading apart from the center.
It's like a geological tape recorder. New crust forms at the ridge, records the current magnetic field, and then gets pushed aside as even newer crust forms. This was it. This was Wegener's missing mechanism.
The continents aren't plowing through the ocean. The continents and the oceans are moving together. They're passengers on these larger plates.
And there was another huge surprise. The age of the ocean floor. You'd think it would be ancient, billions of years old.
Sure, as old as the Earth.
But when they started drilling, they found the oldest oceanic crust anywhere is only about 180 million years old.
Which is nothing. That's incredibly young in geologic terms.
A teenager, yeah. So if new floor is constantly being made at the ridges and the oldest floor is so young, it forces the question, where is all the old crust going? The Earth isn't getting bigger.
Right. It has to be getting destroyed somewhere else.
Which brings us to the full picture. By 1968, we have the complete theory, plate tectonics. But we should clarify what a plate really is. People mix up crust and plate.
Okay, yeah. Give us the plain English breakdown.
So the crust is just the thin chemical skin on the outside, but a plate is a mechanical layer. It's called the lithosphere.
The lithosphere.
And it includes the crust plus the very top, rigid part of the next layer down, the mantle. This whole slab is cool and strong, and it moves as one unit.
And it's riding on top of the Asthenosphere.
Right. The Asthenosphere is the key. It's still solid rock, not liquid magma, but it's so hot and under so much pressure that over millions of years it can flow. Kind of like silly putty or a glacier.
So it's this weak flowing layer that lets the ridge and plates above it slide around?
That's it. So we have these 7 huge plates, like the Pacific Plate and a bunch of smaller ones, all jostling for position on this slowly churning layer below.
Yeah.
And all of the real action, the drama, it happens at the edges.
At the plate boundaries, that's where you get all the earthquakes and volcanoes.
And mountain building. There are 3 main types. First, you have divergent boundaries, where plates move apart.
That's the mid-ocean ridges we were just talking about.
Mostly, yes. But it can happen on land, too. Look at the East African Rift.
Africa is literally tearing itself apart.
It is. The crust is thinning, magma is pushing up. That's why you have volcanoes like Kilimanjaro there. Eventually, that whole piece of Africa is going to break off, the ocean will flood in, and you'll have a brand new sea.
Wow, okay, so that's a part. What about when they crash together? Convergent boundaries.
Here, it all comes down to density. If a dense oceanic plate collides with a lighter continental plate, the ocean plate always loses. It gets forced down underneath the continent.
That's subduction.
That's subduction. The old, cold ocean floor sinks back into the mantle to be recycled. This is the answer to that earlier question. This is where the old crust goes.
And it's not a gentle process.
Not at all. As that plate sinks, it generates massive earthquakes. And the water it carries down with it causes the mantle above to melt, creating magma that rises to form volcanoes on the continent.
Which is why you have the Andes and the Cascade Mountains in the Pacific Northwest, Mount St. Helens, Mount Rainier.
They're all subduction volcanoes. But what if two continents collide, two light, buoyant plates?
Neither one can sink.
Exactly. They're both too light to subduct, so they have nowhere to go but up. They just crumple and fold and stack on top of each other.
Creating the Himalayas?
The highest mountains on Earth. That's India crashing into Asia.
Yeah.
And they're still rising because India's still pushing. That's why you can find seashell fossils at the top of Mount Everest. That rock used to be at the bottom of an ocean.
Which is just incredible to think about. Okay, so we have a part together, and the third type is transform boundaries, sliding past each other.
Right, like the San Andreas Fault in California. The Pacific Plate is grinding northwest past the North American Plate. There's no creation or destruction of crust, just immense friction. The plates lock, stress builds for a century, and then snap.
And you get a massive earthquake.
Exactly.
So this all makes sense. We have the mechanism, we have the evidence, but let's go back to the ultimate why. What is the engine driving all this? We know it's not the tides.
It's a heat engine. Deep down, the Earth's core is incredibly hot, and that heat needs to escape. It sets up these huge, slow-moving convection currents in the mantle.
Like boiling water in a pot.
Sort of. But it's not just a simple conveyor belt dragging the plates along. We now think the plates themselves are a key part of the engine. There are two main forces, slab pull and ridge push.
Okay, what are those?
Slab pull is probably the biggest driver. Remember that old, cold, dense oceanic plate sinking in a subduction zone?
Yeah, the anchor.
It acts exactly like an anchor. As it sinks deep into the mantle, its sheer weight pulls the rest of the plate along behind it.
And ridge push.
That's the other end. At the mid-ocean ridges, the new crust is hot and elevated. Gravity just gives it a little nudge, causing it to slide downhill away from the ridge. So you've got a little push from the ridge and a big pull from the sinking slab.
It connects everything. Plate tectonics isn't just one chapter in a geology book. It's the unifying theory for the entire planet.
It explains the why. Why are there volcanoes in Iceland? It's sitting on a spreading ridge. Why does Japan have so many earthquakes? It's on a subduction zone. It turns the map from a static picture into a living, breathing system.
And it's still happening. That's
Yeah.
what's so mind-blowing. The map we see today is just a snapshot in time.
A fleeting one. The Atlantic Ocean is widening by about an inch a year. The same speed your fingernails grow.
Which doesn't sound like much, but over millions of years.
It's thousands of miles. The Mediterranean Sea is slowly closing as Africa pushes north. The Pacific is shrinking. Far in the future, the Americas might eventually collide with Asia.
forming the next Pangea.
Pangea Proxima, some call it, a new supercontinent. It really puts our human timescale in perspective.
It does. We see earthquakes and volcanoes as these terrible disasters.
And they are, for the people affected.
Yeah.
But from a planetary perspective, they're not disasters. They're the planet's heartbeat.
Without them, the Earth would be dead.
Geologically dead, yes. The carbon cycle would shut down. Nutrients wouldn't be recycled from the deep Earth. The planet would become static, like Mars. So the fact that the ground moves under our feet, that's actually the sign that our world is healthy and alive.
That's a powerful way to end. The destruction is a side effect of the very machine that keeps the whole planet habitable.
It's the engine of life itself.
Well, next time you look at a map, remember, it's just a temporary arrangement. Thanks for exploring the moving world with us on this deep dive.
My pleasure.